Thanks, Ashley, and good afternoon from LI-COR Biosciences. As Ashley said, today's webinar is entitled Designing a Gas Exchange Chamber. And today's topics are really going to focus on design considerations, not so much the actual how-to of building a chamber. The information will be really practical to those designing custom chambers for use with the LI-6400 XT portable photosynthesis system, or those designing custom chambers for use with the LI-8100 soil CO2 flux system, or those designing custom gas exchange systems around any of LI-COR's standalone gas analyzers. Before we get started with the actual presentation, I'd like to pass things off to my colleague Pat Morgan, and so he can find out a little bit more about the audience's interest. Pat?
Thanks, Jason. As scientists here at LI-COR, we're very interested in how customers are interacting with our instruments and building their own custom chambers. We've given you a short list of potential items that maybe you're looking at making a chamber for, but also you can send in other items that you may be measuring through the question and answer section within the webinar.
Thanks, Pat. I just wanted to let everyone know that this is a multiple answer question, so go ahead and select all of those that apply. And if there's not an answer that you're looking for, you can go ahead and submit that via the Q&A function. We'll give just everyone a few more moments to finish answering. Thanks.
As expected, we've seen a fairly large diversity in things that people are interested in measuring, and that helps us as we go to designing the next chambers that may be offered for the different instruments. And with that, I'd like to turn it back over to Jason to discuss some of the things that we include as scientists within our chamber designing.
Thanks, Pat. So we just asked you about what you're interested in measuring, and this is really an important question and the first thing that you need to consider when designing a custom chamber. You know, it's quite possible to measure CO2 or H2O fluxes from a lot of different sample materials, as we've tried to illustrate here. But how you design a chamber is very different for different materials. You know, a chamber designed to measure leaf level fluxes will be quite different than a chamber designed to measure small animal respiration. And so really knowing your sample material is the first thing that you need to consider when you're building a chamber. The next thing to think about is the approach to the measurement. And really there are two basic approaches that are applicable here. One is the closed transient system approach, and the other is the open steady state system approach. In a closed system, gas is circulated in a closed loop between the measurement chamber and the erga. Fluxes are computed based on the change in CO2 concentration over time in this system. And what this allows you is it's really sensitive for small fluxes. So it's able to resolve very tiny changes in CO2 concentration with time. But the main constraint here is that chamber conditions are constantly changing throughout the measurement. So if you're looking at some sort of material where, say, CO2 concentration affects the measurement, then you have quite the possibility for feedbacks in the measurement. And so the actual measurement technique itself is confounding the measurement that you're trying to make. In an open system, we're measuring the gas concentration before and after it passes over a sample. And here the flux is computed from the difference in concentration between these two sample measurements and the flow rate through the system. You know, this has the advantage over a closed system that things are at steady state, but the disadvantage is that the sensitivity of the measurement's limited, and it's limited by the sensitivity of the analyzers and how well matched they are to each other. And if the two analyzers are seeing the same gas and one reads higher than the other one, that false difference is going to appear as an apparent flux. So if we think back to the previous slide, we showed that in a closed system, the flux is computed from pressure, volume, temperature, and the change in CO2 concentration with time. For the range of biologically significant temperatures and atmospheric pressures, the effect of temperature and pressure is relatively minimal on the relationship between the change in CO2 concentration with time, this dc/dt value, and the flux. But for volume, it scales at about 1:1. So for the same flux, doubling the chamber volume will cut the change in CO2 concentration with time in half. So why does this matter? Well, essentially, the larger the chamber, the more the signal that you're trying to measure becomes diluted. And this is important because at some point, if the chamber is too large, the signal will be on par with the background noise of the analyzer. In the example shown here, this is the expected fractional error for various changes in CO2 concentration with time for measurement periods of 60 to 300 seconds, assuming about a 2 ppm peak-to-peak noise in the analyzer. The uppermost line is for a 60-second measurement, and the lowest line is for a 300-second measurement. So you can see that increasing how long the measurement runs will reduce the error, but the effect is much smaller than increasing DC-DT. And well, how do we increase DC-DT? We make sure that our chamber is not too large for the measurement that we're trying to make. So volume is important in an open system too, but for an entirely different reason. Here, volume doesn't tightly control the relationship between the CO2 concentration that you're measuring and the final flux that you're trying to get at, but volume affects how long it takes the system to stabilize after a change occurs. Here we show stabilization curves for chambers from 1/4 liter to 10 liters, assuming 700 micromoles per second flow, which is about the highest flow rate that you can achieve with the LI-6400 XT. It's clear that the larger the chamber is, the longer it takes it to reach stability. And we can illustrate the effect on the measurement with this example. Here we have a 5-liter chamber and 700 micromoles per second flow rate, and have done something that will result in a 20 ppm change in this chamber CO2 concentration. This could be placing an actively photosynthesizing sample in the chamber, or if we're using the 6400, it could be simply asking for a different lower CO2 concentration. If we use the curve in this first figure to model the chamber CO2 concentration, we see that it takes about 1,500 seconds for the chamber to go from initiating the change to the target concentration. If we wanted to calculate photosynthetic rates or a flux using this example, we'd have to wait about 21 minutes after placing the sample in the chamber before the error in the measurement due to this stabilization was less than 1%. The other thing to say about this is that models assume ideal conditions, and that mixing in the chamber is perfect, that there's no competing processes going on. So if you measure how long stabilization takes on a real chamber, it's often longer. In the example shown here, the blue line is what the model would predict for a 0.4 liter chamber at 500 micromoles per second flow. The red line is real data for a chamber of that same size, the same flow rate, looking at water vapor concentrations. And what we see is that there's a big difference between them. And well, what does this difference due to? Well, water is really sticky, and it likes to absorb the chamber walls and anything else in the chamber. And so what this does is it effectively increases the amount of time it takes for the chamber to stabilize, because we've got this competing process. We have water exchange going on with the chamber walls. This sorption effect on the fluxes is basically the same as our earlier example looking at the stabilization of CO2 concentrations. Just like with calculating a photosynthetic rate in the CO2 example, the error induced in transpiration here scales 1-to-1 with the curve shown in blue. The other thing to note with this is that because sorption has to do with interactions between water vapor and the chamber walls, chamber material plays a big role here. These two curves are for two identical chambers made out of two different plastics. The chamber material from the yellow curve is more hydrophobic than that for the green curve, which decreases the amount of time it takes for the chamber to stabilize. In terms of materials to use, acrylics are a staple for custom chambers. They're readily available and easy to work with. However, they absorb a lot of water. In general, cell cast products are better than extruded products, but for either, sorption's relatively high, and you wind up needing to reduce this somehow. And one of the things that we recommend is the use of Teflon film. I think this is a good point to stop and pause and hand things back over to Pat. Pat?
Thanks, Jason. One of the things that does play an impact on the chambers is how large they are, and that will impact whether you need to include additional fans and mixing. So what size chambers are you looking at making for your custom chamber? As expected, we have seen a range in sizes, and there are several things that you need to consider, one of which is the rates that you're actually going to be measuring within your instrument, and Jason's going to speak to those considerations now.
Well, now that we've seen the importance of chamber volume, let's talk a bit about sizing the chamber for the measurement that you're trying to make. This is a separate issue than volume and relates more to the amount of sample that will be measured in the chamber rather than the amount of headspace in the chamber. We're going to run through this by going through an example. And in this example, we're measuring a very happy sunflower leaf in the standard 2x3 clear top chamber that comes with the LI-6400 XT. In this example, we're assuming a transpiration rate of about 18 millimoles per meter squared per second and a conductance of about 1 under full sun conditions. So these are not unreasonable values, but they're pretty high. The curve shown here is the modeled chamber relative humidity given these conditions over a range of flow rates through the chamber. Remember, we're using an open system here, and so flow rate is very important in the relationship between chamber concentrations and transpiration rate or photosynthesis. And what we can see is that at any flow rate above about 250 micromoles per second, the turnover in the chamber is great enough that we wouldn't have to worry about condensing water in the chamber or in the erga. Now, if we did condense water, that would probably end our measurements for the day, and so it's something that we want to avoid. If we take this example further and we apply the same conditions, but this time we're going to assume a custom chamber that encloses an area 4 times as large as the 2x3 chamber. We see that we'd need flow rates above 750 micromoles per second to prevent condensation. You know, the maximum flow rate that we can get in the LI-6400 XT is about 700 micromoles per second. So given these conditions, we wouldn't be able to make this measurement with this chamber on the LI-6400 XT. Now, the point here is not to say that large leaf area chambers can't be used with the LI-6400, as we have plenty of customers that do this. But it's to illustrate that physics and the measurement desired impose limits on what we can do, which prevents there from being a one-size-fits-all chamber solution. So think about what you want to measure before you start building the chamber. I mentioned mixing in a previous slide but didn't go into detail. And I talked about a model assuming perfect mixing. So what does that mean? Well, mixing basically describes turbulence of the gas inside the chamber. In a well-mixed chamber, gas concentrations are homogeneous throughout the chamber because turbulence is such that no pockets of still air develop. So why does this matter? Well, we'll get to that in a moment. One of the things that affects mixing is chamber shape. In a round chamber, it's relatively easy to achieve good mixing, as shown by the velocity diagram for this round chamber. We see that the air is all moving throughout the chamber and it's moving at a pretty even, constant rate. If we take the same example and we assume a square chamber, little eddies form in the corners. We still get good mixing throughout the center of the chamber, but the corners wind up being this pocket of air that's not mixing with the bulk air inside the chamber. What happens is, instead of there being mass flow due to turbulence in the chamber between these pockets and the bulk air in the chamber, it winds up being diffusion, and diffusion is a slower process. And so what does this mean? Well, for an open system, this increases the stabilization time. So diffusion's slower than bulk flow, and so it takes longer for the whole chamber to come to some stabilization point and make the measurement without having errors. For a closed system, since we're in a transient system, we never come to stable, steady state conditions. The diffusion in and out of these pockets causes competing fluxes, and it results in a measurement error. Mixing also influences the measurement in other ways. Typically, when we're sampling gas concentrations in a chamber, we're not sampling the entire volume, but we're pulling a subsample out of the chamber. So it's really important that all the gas in the chamber is homogeneous, because if we're subsampling in a pocket, say one of the eddies in the corner from the previous example, that gas isn't going to be representative of all the rest of the gas in the chamber. So in the example we show here, there are 2 opposing fans in this chamber to increase turbulence. If we sample the air from the point indicated by the arrow, this represents a well-mixed and probably pretty representative sample of the bulk air in the chamber. But with this design, a stagnant airspace is created in the center of the chamber that's not well mixed with the rest of the chamber. Pulling a sample from there could introduce a significant error in the measurement. So, to wrap things up, we've highlighted some key things to consider when designing a chamber, and hopefully you'll find this information helpful. I'd like to say thanks for your attention and hand things over to Pat now for him to wrap things up. Pat?
So Jason has given you a lot of information about designing chambers and the things you need to consider as you design a chamber. We'd like to know how comfortable you are in undertaking designing your own chamber. Please rank your comfort level from 1 being lowest to 4 being highest level of confidence in designing a chamber. There's a range of comfort level in designing a chamber. One of the nice things is LI-COR has a lot of experienced scientists and application analysts who can help you in designing chambers and answering questions. We also have a couple of application notes that you can turn to for additional information. They can be found on the tech support website. They're application notes number 3 and 128, and they provide a lot of information on designing chambers and interfacing those with the 6400 and the 8100.
Thanks, guys. I have a few questions for our speakers to answer. If you've asked a question that hasn't been answered, please note that our panel will stick around until all of your questions have been answered. Okay, our first question is, what is the biggest chamber I can use?
Well, that's depending on which instrument you're going to be using. On the 6400, we have a theoretical limit on the chamber, which is about 2 liters. On maximum size. That's based on the flow rate of the instrument. Much larger than that, and you cannot use the pump within the instrument to control the flow rate and flushing out of the chamber.
But if you think back to the example that we gave in the webinar where we had the 24 centimeter square leaf area in a 4x6 chamber, well, that chamber was much smaller than 2 liters, and we demonstrated that it wasn't practical to make that measurement with that. And so there's a theoretical size limit, but there's also the actual sample material that you're trying to measure, and that imposes limits.
But if you actually look at using a closed system for the 6400 or the 8100, that chamber size can be quite different. You can have very, very large chambers depending on the mixing you have within the chamber.
That's right. With closed systems, I mean, we've seen chambers done that were several cubic meters in volume that had individual fans in there to increase the mixing. But again, you know, it comes back to the sample material, and that the sample material is really what imposes the size limit. With a closed system, you go too big, you dilute the fluxes too much, and you can't make the measurement.
Well, and the other thing you can do is you can actually use the analyzers to make just a subsampling measurement, as Jason pointed out. And if you remember back to that circular chamber with the 2 fans, if you've got a system that actually measures the flow rate in and has adequate mixing, you can have theoretically very, very large chambers in the order of 10 square meters. And if you're just subsampling using the analyzers, you can just take a small amount of air out of the chamber. But to do that sort of thing, you would need to look at application note number 2, which provides more details on those.
That's an excellent point, Pat. Shall we move on to our next question?
Thank you, guys. Our next question is, what materials can I use for chambers?
Hey, thanks for the question, Ashley. And it's a really valid question. I mean, there's a lot of materials out there. Some are better for building chambers. Some are easier to work with. I mean, ideally for a gas exchange chamber where you're interested in measuring CO2 and water vapor fluxes, you want a material that doesn't sorb a lot of water vapor. I mean, the best thing that comes to mind is nickel-plated aluminum, but there's certainly plenty of plastics.
Well, and the problem with that nickel-plated aluminum, Jason, is you're not going to get a whole lot of light penetration to that. So a chamber made out of nickel-plated aluminum is not going to be the best thing for measuring plants. But you're absolutely right. That nickel-plated aluminum is actually what we use on most 6400 chambers, but you have to have some sort of clear orifice to let light in if you're going to be going that route. The other problem is the types of plastic that you use, depending on whether they're extruded or cast, as Jason pointed out, has a real impact on the sorption of the water on the walls, which actually will impact the measurement that you make with CO2.
And that's true. And, one of the things that we didn't point out was that not only do a lot of plastics absorb water, but there's a lot of plastics that absorb CO2 as well. We've seen Teflon materials that take up tons of CO2, and that's really going to mess up the measurement.
The other thing that you have to think about is the surface treatment that the plastics receive. Even if you have a cast acrylic, the problem is if you actually polish that or machine that, you've now put a very rough edge on there, which creates a very porous surface that has a lot of places for water and CO2 to absorb to. So the best thing to do is make some measurements and then also look at lining your chamber once you've constructed it. We have a Teflon material that works fairly well for that application.
Very good, Pat. Shall we move on to the next question?
Absolutely.
All right, thank you. Our last question is, how do I interface my chamber with the instrument?
Thanks for the question. It depends on what instrument you're actually going to be interfacing it with. There are a lot of considerations with the 6400, the 8100, or any of the analyzers. If you're using the 8100 and 6400, you do have some potential for utilizing the pumps and fans within those two instruments. If you're using some of the other analyzers, you will have to look at getting additional pumps and fans to interact with those two instruments.
And then there's the actual physical mounting of the chambers onto the instruments. For the 8100, we have a parts kit for making flash measurements that provide a lot of options for actually interfacing custom chambers to the 8150, so you can operate in a multiplex mode. And the part numbers for that are the 8150-670, and then -8 for the 8-port version, and -16 for the 16-port version.
With the 6400, we also have a kit that lets you interface chambers with the 6400. Now, the limitation with that is you're going to be relying on the leaf mixing fan, so you can't have very large chambers and utilize that kit. That kit is 6400-19.
And with either one of these, the kits come with the application notes that we referred to earlier, but you can get the application notes for free online and look at them, and they provide a lot of good hints on how to interface chambers, and maybe you've already got the parts laying around the lab that you need.
It's possible. So we appreciate the time that you've given us. If you have other questions, please feel free to submit those to us.
Thank you.